Okay, so this is Java, and we're going to look at the fundamental and essential ingredients of Java. We'll give a little bit of background, a little bit of history, a little bit of sort of philosophical perspective on this language um, before we really jump in and learn the programming elements. This is a chart. Do you like charts? I like charts. And what this chart shows is an index to programming language popularity that is maintained by this organization, TIOMB. I don't know how you say it. I'm sure it stands for something. Anyway, you can see they've got several of the big languages listed here at the bottom. And you can see along the this axis that this is over time. So programming language popularity over time is what we're looking at. What do you see at the top? Take a look at this and tell me what trends, what interesting inferences you would make from this chart, particularly in relation to Java, which is sort of the subject of this class. All right, so Java has maintained a pretty strong lead. It's a pretty dominant #1 for most of this time. It does sort of seem to be falling of late. What's C is up there. Austin's pointing out Objective-C. You see the yeah. What's going on there? You know what do you make with Objective-C? You make iOS apps. Mm-hmm. So you kind of see the rise of the iPhone here, represented by the blue line. C++. So that's this gray. You see, pretty big 3 back here in the early 2000s, but it sort of trailed off. I'm really impressed by this C dominance. There's a lot of overlap between C and C++, and so I can imagine that there might be some sort of fluidity as to what a project might look like. This gray is C++. Anyway, so I think this is interesting. Now, this is just one way to slice some data, as in some people might have issues with how this organization computes the index. It's based on, I think, a lot of different factors, like Google searches for a certain language name and a lot of other factors, and they group that all together and create a number and then normalize it to create this. I just think it's interesting. At least a couple takeaways. Even if Java does seem to be fading a little bit, compare Java to Ruby, right? I mean, Ruby is super hot. Everybody, lots of people very excited about Ruby, but still in the whole scheme of things, it's not as big a language as Java, especially because Java has so much code that's already been written. So much of an installed, maintained base of code. So what we're doing here in this class, studying Java, is important. It is relevant. It's one of the big top 3 languages from this index. This is another way to view this data, just in terms of position, and this is the position currently, the position a year ago, and then the change in position from the previous month or year. I'm not sure what the time period on that is. And this is what we saw before, but you do see this rapid rise in Objective-C, actually beating out C++, I think, for the first time. Anyway, so this maybe shows you some languages that are of interest that maybe you want to study and put in your resume, and we may cover it in other courses at this university or not. All right, so let's talk about Java. What is it? What is the essence of Java? I put 3 words here, and these are 3 words that are good descriptions of Java. Java is a general purpose language. General purpose meaning you can use it in lots of different application environments to solve lots of different kinds of problems. Secondly, it's object-oriented. Java is object-oriented through and through. Unlike C++, it is impossible to make a Java program that does not include a class definition. You have to, every Java program has at least one class. All right, so I can't overemphasize how object-oriented Java is. All right, so when we're writing Java programs, we're always writing with an object-oriented paradigm in mind. Looking at objects and methods and data members, fields, properties of an object. That's the way Java works. Thirdly, Java is designed to be a very portable language. Portable means Java programs can be taken from one computer to another computer, from one OS to another OS, and run. Right? Huge emphasis on portability in Java, and we'll see some of the major designs that Java used to achieve this goal. This is the creator of Java, James Gosling, and he created Java some, 20 years ago. They set out with 5 design principles in designing Java and choosing how to, the specifics of this language. And these are the 5, and I tried to highlight the words that are most important about them. Number 1, they thought it should be simple, object-oriented, and familiar. As we've already said, object-oriented is this huge paradigm goal. Right? Everything in Java is object-oriented. They also wanted it to be simple, right? Not overly complicated. Simple's good. Simple's always good whenever you can achieve it, as long as you can still accomplish your other goals. And familiar. And familiar here means it's familiar to programmers. And the way, I think the main way that this was achieved is Java looks and feels like C++. It feels like it's 85–90% C++. Right? It's lines in with a semicolon. Right? The same keywords, probably 60 or 70% of the keywords are the same between Java and C++. So that's familiar. We feel at home in Java if we feel at home in C++. Right. Number 2, it should be robust and secure. Java has a lot of mechanisms in place to make sure that code is executed in a secure way, and that programs can be robust. And we'll talk about a few of those in just a moment. Number 3, it should be architecture neutral and portable. Architecture neutral, what does that mean? Well, that means regardless of what architecture you're on, whether it's Windows or Linux or Mac or any other platform, that shouldn't matter to the running of your program. You should be able to write a program once and run it anywhere. That's one of the kind of taglines of Java, and it generally achieves that. So this emphasis on portability, that we don't have to have a specialized version of the program for different platforms, different architectures. It's highly portable. Number 4, programs in Java should execute quickly, right, with high performance. So we don't want to sacrifice speed by doing all these other design principles. We still want it to be fast. Everybody wants fast, right? Never give up fast. And 5thly, it should be interpreted, that's as opposed to compiled, and we'll see how that kind of is shaken out as well. It should be threaded and dynamic, and we'll talk about those topics later. We'll definitely hit on how Java incorporates in the language a multi-threaded approach, and there's also a lot of dynamic properties of Java that are different than C++ in terms of like reflection, and we'll talk about those later on as well. So what is Java? Well, really, Java is a lot more than a programming language, although that's sort of how we're going to look at it primarily in this class. That's what you maybe think about first. So Java is a programming language. It's syntax and semantics that are required to create a programming language. but it's also a development environment. As a developer, Java gives you a large suite of tools, like a compiler, an interpreter, even a documentation generator, a packaging tool. So from all through the software life cycle, the things that you would need to take a source code and create an executable program, a compiler, Java includes that. How do you run this program? There's an interpreter to run that. The whole development, application and deployment environments, there's some overlap between those, but all those things are included in Java. Java is all that put together. There are actually two. The application environment includes the Java virtual machine, which we're going to talk about more in just a moment, and the deployment environments there are two main ones, which are applications and applets. And applications run kind of more on just a desktop, laptop computer. An applet is the way to deploy a program, but it's running inside the web browser. And I think you've probably seen those on the web as well. So those are two deployment environments. All right, so what are some features of Java? We've hit on several of these already, but I wanted to highlight these one more time. Number one, the Java virtual machine. All right, this is the kind of the software architecture that runs Java programs. Number two, Java's object-orientedness. Java's object-oriented through and through. This is a distinctive and a primary feature of Java. Number three, garbage collection. Garbage collection means that memory is automatically reclaimed, automatically cleaned up. The programmer doesn't have to manually manage memory. The system does it for us, which is nice. But there are certainly trade-offs or anything like that. And lastly, code security. As I said, Java goes to great lengths to keep your program secure and separated and sandboxed, and to keep other people's in the same kind of separated, safe environment. Yes? I want to say mostly no. You live in this system and you let Java take care of that for you, the Java runtime environment. Good question. All right, let's hit on each one of these just a little bit more. So the first feature, the Java virtual machine, what is this about? This is a key kind of principle of the Java environment. This is a very simple diagram that illustrates kind of the layering approach of Java. All right, so we've got our base platform. Maybe that's Windows 7 running on an x86 processor. All right, that's our platform. On top of that, we have our operating system, Windows 7, on top of some architecture. The Java virtual machine, you could imagine as another layer, which is acting like a computer, acting like a platform, acting like an architecture. And this is really, you could imagine, it's sort of a software interpreter that's going to interface between programs, which are up here on top of it, Java programs, and the operating system, the hardware that's underneath. So the JVM is an imaginary machine that's implemented by emulating software on a real machine. It provides the hardware platform specifications that you have to compile all Java code to. Right? Bytecode is an important word in this discussion. Bytecode is a sort of special language that's understood by the Java virtual machine. So when Java source code files are compiled, the result is, you could imagine, an executable file that's written in bytecode. But this executable file won't execute on any real hardware. It's an executable code that runs on the Java virtual machine. So we've introduced an additional kind of layer between your source code and the hardware. why would we do that? That seems like a bad thing. We're adding more layers. We're adding more abstraction. It's a good thing because it allows Java programs to be compiled in a manner that's independent of particular computer hardware. So since all Java programs are compiled to run on a Java virtual machine, then that same program will run on the JVM if a JVM is running on Mac or Linux or Windows or any other platform. You see the beauty. By introducing this independent kind of middle layer, we've separated the dependency between executable files and the hardware, the platform.
So what we're doing is we're changing the JVM between platforms.
Right. So the people who run Java, which would be used to be Sun and is now Oracle, they write the JVM for different platforms and distribute that for free. All right. So as long as your platform has a JVM, a Java code, a Java program, which is going to be compiled down into bytecode, will run on that JVM. And you, the programmer, the application programmer, don't have to worry about what's it going to take to run this program on Linux, because I wrote it for Windows. Right? All of those platform differences do not exist in Java. So really, we're putting a lot of complexity into that JVM, but we get a lot of benefits from it because it does make the upper layers independent from the lower levels. The question? Yes?
So it doesn't matter if any files in the same region. Like if I take it from Mac and I put it on Windows, it'll save them in the same memory. It doesn't matter like Slack or anything like that.
The compiled Java files will work between platforms. Yes. And I think I have an example of that. Let's look at this. Maybe this is better. When we run a program, we're going to run it with the Java command. That's the name of the interpreter. So when we say Java and then the name of a bytecode file, which is really going to be a file that ends in .class, that could run on the JVM that's running on Windows XP on top of Intel. Or it could run on the JVM that's running on Red Hat on AMD. That same bytecode runs on either one. The JVMs are going to be different. The program that is the JVM will have to be specific to the platform. But the program that you write, this Java program that's going to be in bytecode, be compiled to bytecode, is going to be the same executable for each JVM. Does that make sense? And Java was really sort of, I think, the first big language to do this. Now, if you've had any .NET classes like you may have had here, you know that .NET follows the same model. And .NET introduces that intermediate language, the .NET CLR, the Common Language Runtime, and that's similar to this Java virtual machine. But really Java was first, so this is how Java does it. We've got the JVM as this middle layer, and it makes this virtual machine is the same to programs above it, even though it's different kind of below. I don't know. It takes up resources. It takes work to do that, but that's, I think, highly optimized because there's a lot of incentive, there's a lot of payoff to make that work well. We could look into that. That'd be a good topic for a student presentation, I think. Okay, so I know this is hard to see, but the cool thing about the JVM is it ends up being very versatile because in some sense what the JVM is it's a new computer. It's just sort of a virtual computer, right? It happens to run on top of a real computer. But you can do lots of different things with this. So in the normal process, we're going to take Java source files, and those end in .java. We will send them to the Java compiler, which is called Java-C. And what that compiler outputs is bytecode, which are files that end in .class. So this Java bytecode is actually kind of a series of machine language instructions, but the machine that they're instructions for is the JVM. Not an Intel computer, but the JVM. And then we can run, say, this Intel x86 JVM, that version of the JVM can run this bytecode, and it knows how to interface to a particular platform. All right, this is called the Java runtime environment, the JRE, all this bottom layer, which we're thinking of as the JVM. But there's other things that have to go on here too as well. The memory manager, the garbage collector, and the interpreter, or the just-in-time compiler, kind of the guts of the thing that actually make this bytecode run. All right? So this is kind of our normal development environment. This is what we're normally going to be doing. Okay? Does this picture make sense? All right, well, here's the cool thing. This system is versatile enough that we could actually create we could use other languages like Python and run this Python script through a program that converts it to Java bytecode. And there's a program that does that. It's called Jython. Yes. But you see at this level, these green files, even though they're the implementation, the conversion of Python source files to Java bytecode. But once you've got this Java bytecode, right, that's the same. And you can run that on any JVM. This JVM that we were just looking at, the x86 JVM, or if we had a JVM for the ARM architecture, you know ARM, it's on a lot of mobile phones. That's the hardware for a lot of mobile phones. If you had a JVM for ARM, it could also run that program, whether that program was from Java originally or from Python. So because we kind of have this level of decoupling, we've decoupled that bottom layer from the top layer, and we have this common middle layer that gives us a lot of versatility in terms of multiple platforms or even multiple source languages. And actually there's a huge number of new languages that use the JVM as their execution environment. And we may look at some of those later on in the class. Yes. All right, back to our key features of Java. Java is object-oriented. What is object-oriented about? Well, everything in Java is an object, with just a very few exceptions. But everything is object-oriented, and you're going to have a lot of difficulty. It's going to be impossible for you to write a program that doesn't have an object, a class involved. Unlike C++, which kind of C++ allows you to use objects, but you can also program procedurally or imperatively as well. You can just have a list of instructions that run in a function that aren't in a class. You're not going to do that in Java directly. All right. Java supports, encourages what I like to call object-oriented Pi. Do y'all like Pi? I love Pi. In this case, Pi means polymorphism. So that's the ability to treat objects in different ways depending on the circumstance. The object kind of morphs into the right shape. It supports inheritance. Inheritance is the ability to pass along attributes to kind of children classes. And that supports code reuse. And lastly, it supports encapsulation, which is a way of keeping things that ought to be together and keeping them protected from the outside world. And we're going to spend a lot of time on these three things, as in there are whole chapters devoted to them. So this is just an introduction. We'll come back and talk a lot more about them later. Java supports garbage collection. What is garbage collection? It means automated memory management. This is as opposed to manual memory management. If you've worked in C++ with dynamically allocated memory, if you use the new keyword, then you know that you will have to manually, some point later in your program, use the delete keyword to make sure that you release the memory that you dynamically allocated. And if you have unbalanced news and deletes, then you're going to get yourself into trouble because if you don't delete memory that you allocated, you'll leak it, you'll lose it. And over time, that could be very catastrophic to your program if you were to use up all the memory. Java says that this activity should not be a concern of application programmers. And it goes behind the scenes in the background and collects your garbage. It looks for memory that's no longer being referenced and frees it without the programmer having to deallocate the memory themselves. So it's really about making programmers happy, and not just happy, but more productive and making better quality software. So that's garbage collection. For the most part, it's going to be something you're not going to think about it, but it's going on behind the scenes to help you out. You use objects how you want to use them, and the GC system will figure out when those objects can actually be freed. All right, the last element here is code security. The Java runtime environment achieves security through its implementation of the Java runtime environment. So there's a very structured, controlled way that Java programs are executed. Right? They're in a very controlled environment, which is the JRE. A couple of elements, a couple of pieces of that enforce security. One is the class loader. This is responsible for loading all classes needed for the Java program. And it adds security by separating the namespaces for classes on the local system from classes that access network sources. So there's this there's this wall of separation between things that run locally and things that can access outside. So that gives you enhanced security. There's a lot of other stuff that we could spend a lot more time on related to this, and I don't want to get too detailed, but a lot of this is things that maybe you won't even know would have been a security hole, but a lot of people spend a lot of time finding and addressing security holes, and they're fixed right here at such a level that your program can only exist in this environment. So there's no way of kind of bypassing the rules, because you have to run on the JRE, in the JRE. Even things like the memory layout of the executable is determined ahead of time and is set and can't be changed. If you can do stuff like that, if you can change the memory layout, which you could maybe in a machine that runs native, in a program that runs natively like C++, then you can possibly do crazy stuff. If you can determine where things are placed in memory, and maybe you can put an instruction in a place where it shouldn't be, then you can take control of the system. The second thing is this bytecode verification, and this is a system that will test the format of code fragments and check for illegal code that would violate access rights. Right? So access rights are enforced, and we can verify that this bytecode is safe and it's executing safe instructions. And lastly, there is this sandbox execution, meaning every Java program is going to live and exist in this sandbox, and it kind of has to stay in its own sandbox, and it's protected from other people's sandboxes. Does that kind of make sense? All right. And this would be a great topic for further research as well. For our research project is looking more deeply into this code security in Java. A lot of really neat things, really neat design went into Java's code security. All right, since most of us, or most of you came from C++, I thought it might be interesting and helpful to look at a philosophical comparison between C++ and Java. How are they different or the same? C++ is designed to be somewhat complex, but very, very powerful. Java, on the other hand, from the get-go, was designed to be simpler. Now, we still have to solve some of the same problems, but there's an emphasis on simplicity in Java. Secondly, C++ really has a strong emphasis on performance. C++ enables you to write the fastest possible code. On Java, as we've seen, performance is a goal, but portability is also an important goal, just as important. We want to be able to move programs, even compiled programs, to different architectures. That connects with these next things that I've written. C++ adopts the philosophy of write once, compile anywhere. So C++ requires you to have a compiler for any architecture that you want to run your code on. Take your C++ code and compile it for that architecture. Java, on the other hand, supports write once, run anywhere. Once you've compiled your code, it should run on any platform that supports the JVM. C++ gives you native access to the platform. So when you're accessing the abilities, the functionality of your hardware, you get direct access to it. With Java, you've got to go kind of indirectly through the Java runtime environment and that Java runtime system, right? Because you do have that middle layer, the JVM, that's separating you from the actual hardware. C++ has a fairly basic standard library. That is, there aren't a huge number of built-in libraries and objects to handle issues. Java, on the other hand, these kind of go together. In C++, then there's lots of external libraries that you would use to solve those problems. Java adopted the philosophy that a lot of these core functionality libraries ought to just be in the standard library. It's included in Java. So if you want to do networking in Java, that's built in. There's a library for that that's like the standard library built into Java. Whereas with C++, you would be more likely to go out and find a networking library that's external, third party, that you would use and incorporate in your application. So these things kind of go together. You see how they're linked. Okay, questions on this? All right, well, let's look at how we create identifiers in Java. This is a simple thing, but very fundamental. The rule is these characters, letters, underscore, and $, can be the starting character, and subsequent characters of an ID can also include digits. So what an ID is anything that has a name in Java, like a variable name or a method name or a class name. Yeah. So my takeaway is don't start IDs with digits. So these would be legal IDs, myvar, underscore top, up, max size. These would all be illegal IDs, and you would get a compile error if you tried to create a variable called 12x. All right. Let's look at just a bare bones, simple Hello World application in Java and walk through it. This is Hello World in Java. Let me walk you through it. The first piece that you'll see is, well, first, I think you'll see a lot of syntax that looks like C++. Right, so you're familiar, you're at home, nothing scary going on here. The first thing you'll see is that we have written a class, first of all. So there's an object, which we've named, there's a class called Hello World App. And this class has one method in it. You know, in C++, we call this a function usually, but when we have an operation that's a member of a class, we call it a method. This method is called main, and you see it even takes in some arguments to main. This is a parameter to main. We'll talk more about this later. We see that main has a return type of void. That's familiar from C++. And it has a couple of other words that modify it, and we'll talk about what those mean later on. Inside main, we're calling another method, and this is a method that we access by saying system.out. So it's in the out object that's in the system namespace, and we're calling println. So println is really is the name of the method, and we pass in a string literal, which is just some characters in double quotes. Notice our lines end in a semicolon, and you'll see we've got curly braces surrounding the method and the class. So this is how we would print out hello world in Java. It's a pretty straightforward, I think, program that's not drastically different than what you've seen in C++. Any questions on this code? I know we kind of skipped over some pieces right now. Okay. Let's take another example here. They're just looking at basic math. This should look just like C++ to you. Notice we've got the same outside part here. We've got a class that has a public static void main. Right? We've got a main method that's going to run, and inside main we declare two variables, an A and a B. We initialize them to values 21 and 2. We have a variable answer that we set to be equal to A times B. Right? All this is legal C++ C code. And then here we print it out using our system.out.println. Notice we see one new thing here, which is we have strings, and we're concatenating, we're adding on our answer into this string using the plus operator. And so that's actually creating a new string that will show what the answer is. So this would say, all right, the answer is 42. We'll get you one more kind of taste of Java, and we are going to come back and look at all this in much more detail in subsequent chapters. This shows a for loop and an if statement. And what I would like you to see is this looks just like C++, right? If you know C++, and I hope you do, there's nothing new going on here. This is understandable. We've got a for loop, and it takes an iteration integer variable from 0 to less than 10, increments it by 1, and then we have an if statement that does I mod 2, and if that's equal to 0, right, then it's an even number, and we print that out. And then we end our for, end our main, end our class. So these are some basic constructs demonstrated just very briefly to give you a taste and a feel for Java. Questions on these examples? Okay. As we begin to wrap up, I wanted to end on this note. These are the Java keywords, which look a little overwhelming when they're all displayed in this huge table. What's a couple points of interest to me. Number one, those two that are in green, or in blue, are keywords, meaning you can't name a variable goto, because they're keywords. They're reserved for use by the Java system, but they're not used. So the takeaway is the Java designer said you can't use the word goto in a statement at all, and we're not going to support gotos. Don't try to use it, and don't write a variable called goto or a method called goto, because that's confusing. Also, const is also like that. Which is sort of interesting. So they were kind of reserving and excluding those identifiers. The second thing that's interesting to me is keywords in Java that are keywords in C++, and that's what I put in brown there. And you'll see that's a huge number. So for the most part, even in the keywords, you've seen these before as a C++ programmer. There's a lot of familiarity. Perhaps some of these are pretty specialized and you haven't used them much. Maybe, I don't know if you maybe not use volatile very much, but it's in C++, it's in Java. So learning Java is not hard as a C++ programmer. There are some new pieces, but for the most part you're working in a familiar environment. The takeaways from this lecture is that we've learned about some of the key design features of Java. We've seen how the JVM works, which is really how the Java programs operate, how they're compiled and executed. We've seen some of the basics of object-orientedness in Java, of job security, of garbage collection. And then we ended with those few examples and these keywords.